In our last meeting, I defined a new quantity of our physics, that is the momentum, the quantity of motion, because Isaac Newton had realized that it's not just about the velocity, but also the mass. So we create this new quantity called the momentum. It is the mass multiplied by the velocity. That is very, very simple. You just have to be a bit careful, and I'm going to reiterate this over and over to the point where I might become tedious about it, but you have to be careful that the momentum, because it's defined in terms of the velocity, is a vector quantity. It's not a problem. If you're going in the positive direction, you have positive momentum. If you're going in the negative direction, you have negative momentum. It's just that simple. The only way that you get in trouble is to decide not to worry about it when you're trying to solve a problem. Just like all of our physical quantities, because ours is a universe of change, the momentum can change. A change in momentum is called impulse. I don't want to stress this too much because it's a difficult idea to get your head around, but a change in kinetic energy is called work. It gets a name. The change in kinetic energy is called work. I'm doing something very symmetric here by saying that when a change in momentum happens, the change in momentum is called impulse. So my momentum is equal to the mass times velocity. And you see here the familiar harpoons. I put a harpoon on the quantity just to remind me that it's a vector quantity. We'll discover as we go along. I'll drop the harpoons once we're fully convinced that it's a vector and that we should always be thinking about that. So a change in momentum would be calculated just like any other change quantity. The final momentum minus the initial momentum. That's what change quantities are. Final minus initial, that's the way it always goes. So you see here, I'm calculating m times v, where I'm using the final velocity to calculate the momentum, and then minus m times v naught, where I'm using the initial velocity to calculate the momentum. Final momentum minus initial momentum, and we have a name for that. It's called impulse. Just an algebraic observation that'll help you in your problem solving. These two masses, of course, are the same, because when I'm describing a change in momentum, I'm usually doing that in the context of a particular object whose momentum is changing. So what I've done just for fun algebraic jiggery-pokery is I have factored the m out and left my change in velocity in parentheses, because this is the final velocity minus the initial velocity, which is the change in velocity. So I can write the impulse delta p as the mass times delta v. Now when it comes to the vectorness of this, you have to be very careful, because when you're calculating this change quantity, you will find yourself subtracting, because that's how change quantities work, the final minus initial. So if the final velocity and the initial velocity, or the final momentum and the initial momentum, are positive quantities, then to calculate the impulse, you're going to subtract. But imagine, just for a second, that the initial velocity is -5, and the final velocity is 5. Ooh, same velocity. No, not same velocity. The initial velocity is -5, the final velocity is 5. Then when I calculated the change in velocity, it would be the final velocity, 5, minus the initial velocity, -5. So it would be 5 minus -5, which is 5 plus 5 is 10. So when it comes to getting right answers and scoring points, a student of physics has to be careful, not only to take care of the number of meters per second or the number of kilogram meters per second involved, but also the sign of that. So we need to be careful about that whenever we're calculating something. I had mentioned that Isaac Newton didn't show a particular interest in acceleration, that he always talked about these things in the context of the quantity of motion. Well, what I can do is sort of make a new form of Newton's second law and write it in terms of momentum. Here it is, very familiar. The sum of all the forces is equal to the mass times the acceleration. Everyone knows Newton's famous law. But we also know that by definition, the acceleration is the change in velocity divided by the time in which the velocity changes. So I just make that substitution there. Well, imagine this m sits up in the numerator. The numerator here is then the mass times delta V, which is the change in momentum. It is the impulse. So I could just as well write Newton's second law this way. As a new student of physics, you might be thinking, well, I don't need more Newton's second laws. I'm fine with what I have. Well, just like the law of conservation of energy, looking at the world in this different way is going to make it possible for us to solve problems that we could not solve before. So there's a good reason to do it, even if it might seem at the moment redundant. What this equation says is that the sum of all the forces that act on a thing will change its momentum in time. That mathematical notation describes that simple statement that forces change momentum in time. The impulse momentum theorem is a relationship very much like the work energy theorem. Recall that work is the force times distance. And when I discussed work originally, I suggested that the work describes how a force changes the kinetic energy in space, which is a very heady way of describing this simple idea. The work is the force times distance, where distance is a description of from here to there. Distance is a description in space. Well, the impulse, it turns out, is the force in time, is a description of a force acting in time. Here's how it works. Here's my new version of Newton's second law. The net force is equal to the change in momentum over the time, the impulse over time. And I'm just going to do the simplest algebra to this, multiplying the dt to the other side of the equation so that the change in momentum is equal to the net force times delta t. That equation, delta p is sigma f delta t, is known as the impulse momentum theorem. Just like the work energy theorem that says that delta k is equal to sigma f delta x, this is the impulse momentum theorem that says that delta p is sigma f delta t. I want to pause just for a moment to point out that this implies that the impulse, which is a change in momentum in kilogram meters per second, is fully equivalent to a force multiplied by a time. Well, forces are in newtons and time is in seconds. Last time when I introduced the momentum as a physical quantity, I said it would have units of kilogram meters per second and there was no more fundamental unit. And that's true, but it turns out that a Newton second of momentum is equivalent to a kilogram meter per second. You can use either one, completely correct. You can say that the unit of momentum is the kilogram meter per second, or you can say that the unit of momentum is the Newton second. They are equivalent, not one is more right than the other. I personally always use Newton seconds for momentum. I think I find it more aesthetically pleasing, and I also feel that it looks less convoluted than comparing kilogram meters per second, and then over here I have some kilogram meter per second squared, and then over here I have some kilogram meter squared per second squared. They all look sort of similar. This is very distinctive, the Newton second of momentum. So going forward, that's the unit that I'm going to use for my momentum. Now this is all very fancy, the net force multiplied by delta t. That's a bit sophisticated. If we imagine that we only have one force acting, to simplify things, that we only have one force acting, or that we understand in all cases that the force that we use has to be the net force, and instead of using delta t very fancy, use t, then I have this very simple relationship. Let's let this, for our practical purposes, let's let this relationship, delta p is f times t, that delta p is f times t, let's let that be our impulse momentum theorem going forward, which describes how a force changes the momentum in time. Very, very simple idea. So a couple of examples of how this might be relevant, not only to solving problems, but to everyday life. Here is a truck speeding along, and it has some momentum by virtue of having a mass and having a velocity. And in order to stop the truck, we are given two options. We can either stop the truck entirely by having the truck plow through this haystack here and come to rest, or hit this wall and come to rest. When it comes to the choosing, everyone, even with no background in physics, knows you're going to choose the haystack. But from an impulse momentum theorem point of view, the reason why you choose to hit the haystack is that the haystack increases the amount of time that the momentum changes. There's nothing you can do about the momentum change. You have momentum, you're gonna lose it. That's what the change in momentum is. But by hitting the hay bale, you increase the time so that the force can be small. As opposed to hitting the wall, where the force is large, but the time is small. Large forces are dangerous. Human beings generally have time to spare, but we don't do very well under the influence of large forces, which is why we use airbags. If you're in a violent car accident, you're traveling along down the road, you have a mass, you have a velocity, you have momentum. But then you strike either a movable object, another car, or potentially an immovable object, like a tree. And your momentum is going to change very rapidly. What an airbag does is it's not that airbags are soft, which is not the appropriate description of this. What an airbag does is, just like the haystack, it increases the time over which your momentum changes. By increasing the time, you decrease the force. Hopefully, decreasing the force to the point where it's a number of newtons that don't do injury to the face and head and upper body of the passenger in the car. When forces are acting over very short intervals of time, like this golf club hits a golf ball, the time of impact is extremely short. If you're standing there watching it directly, you don't even see it happen. It's faster than human perception. But you don't have to go too far on the internet to see videos of this sort of thing where impacts happen on a super high-speed camera. There's many frames per second. And then you can see this interaction happen in slow motion, but the time is incredibly short. And so the forces involved are extraordinarily large. The fifth graph fact. I'm rather enjoying this. This is the first time I've ever referred to this as the fifth graph fact. The first of which is that the position-time graph, the slope of the position-time graph is velocity. The slope of the velocity-time graph is acceleration. The area under the velocity-time graph is displacement. The area under the force displacement graph is work. And now, I've made here a graph of force, measured in newtons, of course, as a function of the time measured in seconds. And you see here, generally, the force increases for the first 2 seconds, remains constant until about the 5th second, and then it decreases a bit slower than it rose in the first place, down, and is all done by 8 seconds. Because the area under this graph is force times time, the area under this graph is impulse. I can't tell from the graph what the momentum is. But I can figure out how much it changes. A fun little trick of using a graph like this is they give me these nice little dotted lines. So each one of these blocks is 1 Newton times 1 second. Each one of these blocks is 1 Newton second of momentum. So here, in this first bit, from 0 to 2, under the triangle, I have 1, 2, 3, 4 is the square, cut in half is 2. So between 0 and 2 on this graph, there are 2 Newton seconds of impulse. Between 2 and 5, there are 1, 2, 3, 4, 5, 6 Newton seconds of impulse. So now I'm up to 8 Newton seconds of impulse when I come to the last part of the graph here, which is, you can see this rectangle here is 6, but it's divided in half, so it's 3. 11. So I end up at 8 with 11 Newton seconds of momentum change. Cannot know the momentum from the graph, but I can determine the change in the momentum because the area under the force time graph is impulse, our fifth graph fact. This is a classic observation, a classic question of physics. We can be reasonably sure that every physics student in the world, in any language, is going to encounter this question. Here I have a wall, and what I'm going to do is throw a ball at it. You can imagine it's a super ball, maybe. The ball collides with the wall and bounces off. And I'm telling you that I've measured its mass and I've measured its velocity, so it has 5 Newton seconds while it's traveling at the wall. 5 Newton seconds of momentum headed for the wall. Now here, this oddly shaped bit, same mass, same velocity, also has 5 Newton seconds of momentum. But it's a glob of putty. It's flexible and deformable, gooey even. So it's not really the same thing. When the super ball hits the wall, it bounces off. And an observation I think that we've all made is that it bounces off very enthusiastically. Its momentum changes. No, Shadi, you say it's 5 Newton seconds, it's 5 Newton seconds. The momentum didn't change. Yes, it did, because momentum is a vector. It may not have changed in magnitude, but it did change in direction, and that matters. So if I want to calculate the change in momentum, I need to find the change in the mass times velocity. The final momentum, which if I choose the rightward direction to be positive, then the initial momentum is positive and the final momentum is negative, as I've indicated on the diagram here. The final momentum is negative 5 Newton seconds. The initial momentum is 5 Newton seconds, so here I have this situation I warned about. It's negative 5 Newton seconds minus 5 Newton seconds, which in a quirky sort of way is addition. It works out to be negative 10 Newton seconds worth of momentum change. Negative momentum change? Does that make sense? Negative momentum change? Well, the change in momentum is in the same direction as the force. And what direction does the wall exert its force on the ball? To the left in the diagram, which is the negative direction. The force is in the negative direction. It's the force that the wall exerts on the ball is in the negative direction and creates a negative change in momentum when the ball bounces off of it. Negative 5, minus 5, negative 10 Newton seconds of momentum change. It's a different situation with the putty because the putty hits the wall and stops. Now the trick to this is sometimes folks get it in their head that if a thing stops, its momentum has changed the most. So this is very often a multiple choice question. A rubber ball and a wad of putty hit a wall, the rubber ball bounces off, the putty sticks. Which one has the greater change in momentum? Well, let's calculate. The putty had the same mass and velocity, so the same 5 Newton seconds of momentum going at the wall, and then whammo, it sticks. To calculate the change in momentum, I'll take the final momentum. The putty sticks to the wall. Its velocity is 0. It has no momentum. Stuck to the wall, not moving. Sure has mass, but its velocity is 0, so it has no momentum. Minus the initial momentum, which was 5 Newton seconds, same mass, same velocity as our rubber ball, and negative 5 Newton seconds of momentum change. Its momentum changes, but the ball bouncing has a greater momentum change. The ball bouncing has a greater momentum change. I don't know if it's true, but if these two collisions take place in the same amount of time, then the rubber ball experiences more force than the putty does in the collision, and the greater momentum change.